Perfect. All right, so let's do this. Let's switch to my presentation. So, welcome to my first tech talk. My name is Tristan, and I'll be speaking about IPv6. This talk's main focus is going to be on restoring the end-to-end connectivity model on the internet, which is a fundamental design paradigm of IP networking. It's been broken for a very long time, about 35 years. I think that's about accurate in most IPv4 deployments in the world, and I'm going to talk about why that is. So I'm going to start talking about the basics of IPv4 and IPv6 and just how the internet works in general, just to make sure we're all on the same page. Then I'll address the pain points of IPv4 and how IPv6 addresses those. And finally, I'm going to talk about what others are doing in IPv6 right now and how you can jump on the bandwagon. So IP networking in general is a vast and expansive topic, and it can get pretty complicated. So I'm just going to deliberately skip over a lot of nitty-gritty technical implementation details and focus on simplified rundowns and give you the important takeaways. So I've got a very brief timeline here, which is that in 1981, IPv4 was officially released, and later on, in 1999, we realized that we needed some improvements to IPv4, so we came up with IPv6. But unfortunately, I mean, it sounds like it's been out for a long time, but you might have not heard about it because it's just nowhere near the adoption level of v4 yet. So let's talk about what you should know about IPv4 just very basically. I'm sure most of you are quite familiar with IPv4 addresses in general, and that you might not even have seen IPv6 or heard of it yet. So IPv4 addresses are just 32-bit numbers. They go from the range from 0000 to 255.255.255.255. That's just a more friendly way to represent the number 4 million, 4 billion, 4.3 billion, whatever. That's how many addresses there are uniquely. And just briefly, I'm going to show you how we break those down, because that's a really big address space. And obviously, we don't use that all in one network. We use it in small subnetworks called subnets. We create divisions based on a subnet mask, which is the amount of bits that are masked off the end of the address. I found this really useful graph to show you how that works. We use CIDR notation, which is like slash a number, and that number is the amount of bits that we mask off to denote how we split this network. So for /8, we keep 8 bits and we mask off the rest. For this 8-bit here identifies what our network is, and the rest is what's inside the network. We use the same notation in IPv6. So I'm going to talk about the structure of the internet also. It's common for people not to think much about the architecture of the internet and just see it as a big cloud on the other side of the cable that's going to the internet service provider, but it's actually a lot more interesting like that. The internet is not a single entity, but it's actually a ton of small interconnected networks, as we're going to see. And the network traffic travels end-to-end by crossing many different networks. The internet is a global network where a service provider join at IXPs, or internet exchange points, and literally go into rooms where all there is in the room is routers, and providers plug themselves into each other, and they just create this really vast and expansive network. And because there are so many interconnections, traffic on the internet can take many different paths through different service providers to go to the same destination. Although generally we try to optimize those paths so that we can get to the destination in the shortest amount of time possible and the shortest amount of hops between different networks. So if we go into 2 different countries and access the same website, we're going to take 2 different paths. That's fundamental to how the internet works. If we look at it from a physical point of view, we can think of all these submarine cables, which represent different paths on the internet that we can take just between continents. But then it gets a lot more complex when we look at the logical view of things, what happens in those cables. We find out that interconnections on the internet are even more spread out. So different internet service providers are identified by ASNs, autonomous system numbers. Those are the numbers in the gray circles there. So each number there represents like an internet service provider, and we can see that they're all connected to each other. And essentially, all of these autonomous systems, they have routers that speak a protocol called BGP, the Border Gateway Protocol, and they talk to each other, and they tell each other which routes that they can route, which networks they represent. So everyone tells each other, hey, I have this subnet, I have that subnet, and using that information, we construct what's called the global routing table. Routers form paths between each other to deliver internet traffic to the destination as efficiently as possible. We find paths through different routers who take the least amount of hops to get to the destination. So when we think of this, if you're starting from here and you're going out to there, there's not just a cloud in the middle that's connecting you two together. You're actually going through many different service providers. And if we go even deeper into the nitty-gritty, it looks something like this. The other image was just for demonstration purposes, but this is what the BGP routing table looks like for the country of Canada. So as we can see, there's a lot of different ISPs, so much that they're all overlapping. Those are what the numbers are. You'll notice there are big providers in the middle, which are called transit providers, that interconnect smaller networks to each other. We can see the biggest one here, AS577 in this case, is Bell Canada, and I'm not sure what the others are, but it doesn't really matter. It's just to explain how your traffic gets from one end of the internet to another end of the internet. You go through many different networks. And I talked about the global routing table. What the global routing table is just a table where everyone's subnets that they have advertised on through the routers gets summarized into, and routers use this table to determine where they send their traffic to. And the routing table is limited in size, so when you advertise lots of small subnets that can be summarized into a big subnet, they're summarized. It's like compression, but it doesn't really matter. I just added that for semantics. So now let's talk, now that we've gone through what the internet is, let's talk about IPv4 specifically and what the pain points are of IPv4. So the biggest pain point is address exhaustion. Like I said earlier, there's about 4.3 billion addresses in IPv4 because it's a 32-bit integer. But we'll see that the world population right now is around 8 billion people, and there are at least that many devices on the internet. Just think about how many internet-connected devices you own, like a phone, Internet of Things devices in your house, your smart lights, all of that. Those all consume IP addresses. So there are only 4.3 billion addresses in IPv4, and I think you'll start to see the problem. So back in 1994, the internet was already seeing widespread adoption, and it became clear that there just weren't enough addresses in IPv4, and that we were going to run out, and if we were going to allocate one IPv4 address for every device, that just wasn't going to scale. And this is where the talk about end-to-end connectivity comes. We'll just have to define that. Just a quick note. And what I mean by end-to-end is that every host on the internet can reach another host on the internet. So if I have an IP address and I want to communicate with someone else's IP address, I need to be able to communicate with them directly, and they need to be able to communicate with me directly. In essence, we need bidirectional communication. And this is the principle that empowers peer-to-peer applications. If you think about video calls or voice calls on the internet with WebRTC or BitTorrent file transfers, those are all protocols which require end-to-end connectivity to work optimally. Both sides of the connection need to be able to reach each other without a server in the middle. So, it looks like I've got something a bit ugly in my presentation here. We'll just ignore that. Unfortunately, the answer we came up with was not switch to IPv6. The answer we came up with was NAT, or a network address translation. So to save IP address space, we decided that we were going to reserve certain IP address ranges in RFC 1918, which is a standards document that was published, which reserved these ranges here, which are 10.0/8, 172.16/12, and 192.168/16. I'm sure you've all heard of these IP address ranges because you're probably using one of those in your internal network right now. So what these addresses allowed us to do is to use so-called private addressing inside of our network for services we judge that don't need a public IP address. And then we translate to a shared IP address on the outside, which allows us to save a lot of space when you think about it, because all of the devices on our inside network, they only share one single IP address. And if that doesn't sound bad enough, it gets worse, because internet service providers realized that they also didn't have enough IP addresses to give out to all of their customers. So they added another layer of NAT called carrier grade NAT in between customers' routers and the internet. So you already have a private IP address inside your network, but then your router doesn't even get a public address. It gets another private address, which is in the range 10.64.0/10. And then what happens is that it gets translated again on their network. So you end up with thousands of customers, or hundreds or thousands of customers that share the same IP. I'm just going to go back to NAT here and explain how it works, because I just missed a slide. So a picture is worth 1,000 words. So I came up with this picture here. I believe it's from Wikipedia, and I'm just going to explain what's happening quickly. So we have this host here with the 10.0.0.1 IP address, and a server on the other end with the 200 IP address on the public side. So what SourceNet does is it takes when this host here is communicating with an outside address, it couldn't just communicate with this inside address of 10.0.0.1, because if it sent that to the server would say, hey, I need to send the information back to 10.0.0.1. But as we know, there are like millions of 10.0.0.1s or whatever on the internet. They're not public addresses, so we can't do that. So what the router does is it replaces the 10.0.0.1 with its own IP address, and then the server responds back to the router, and the router then sends the traffic back to the host. And the big problem with this kind of NAT is that it breaks the fundamental principle called the end-to-end principle, because as far as the server is concerned, all the hosts behind the NAT can reach it. But the server cannot directly reach this host behind the NAT anymore. And as far as the server is concerned, all of the devices behind this NAT are identified by the same IP address. So there's no way to easily, uniquely identify all of the hosts behind this NAT. There's also the opposite called destination NAT, which might be easier for you guys to digest because it's widely referred to as port forwarding. I'm sure many of you have already messed with this at some point in your router's settings. because basically it's impossible for outside clients to communicate to servers in your local network because they have a private IP address. So because of that, we need a translation on the router that will map a port on the router's external IP address to a port on the router's internal IP address. This is sort of a band-aid fix for breaking the end-to-end principle. So it allows remote clients to still connect into your network, but the downside is that you're limited to a number of ports on one IP address. So what if you're running multiple services that require the same port, like a web server on port 80, 443, or an SSH server on port 22? If you have a lot of these behind your NAT, you're going to realize that you only have one of those ports on the outside, so you're going to have to use a workaround, like use a different port or something like that, which might be non-practical. So back to carrier grade NAT here, it's the same principle, except like I said before, it's worse because your router here, which would be the CPE, does not even have a public address. So this port forwarding trick wouldn't even work because you would need a port forwarding also on the internet provider's CGNAT to port forward to yours, and then you would have to port forward again, which is not practical. So when you're behind a CGNAT, it basically means that you cannot host servers on your connection unless you use tunneling tricks, which are out of the scope of this presentation for now. So now I'm going to talk about IPv6 basics. IPv6 to the rescue. The biggest selling point of IPv6 is that it touts a whopping 340 trillion IP addresses, which is, if you think about it, way more than the 4.2 billion in IPv4. In fact, I wrote trillion because the number is so big that if I tried to write it on the slide, it would probably take multiple lines. But anyway, since there are so many more addresses, obviously IPv4's way of writing addresses doesn't apply because there's so much more information. So IPv6 addresses are 128 bits in size, and they range from 0 all the way to FFFFF. The notation's changed a bit to cope with this. So now instead of being divided into 4 octets from 0 to 255, we have 8 octets from 0 to 65,000, and we've written them in hex to save space, so from 0 to FFFF. And it's important to note that IPv6 is not just IPv4 with more addresses. There are also a lot of other goodies included. So we have support for multiple addresses on every interface. This is also possible in IPv4, but it's mandatory in IPv6. We have a simplified packet header, which just means that hardware like routers can process the packets more efficiently because there's less stuff to process. We have address auto configuration, which I'll talk about soon, duplicate address detection, and other goodies. So IPv6 addresses might look a bit daunting at first because of their length, but rest assured that they can be shortened. What should I call this? A patch of zeros can be shortened. They can, so we can see all these zeros here. They can just be clamped into 2 colons, and any leading zeros can be dropped. So this address looks pretty long at first, but when we simplify it, it can be much more pretty or whatever. And there's a lot of people who criticize IPv6 because addresses are harder to remember, but you shouldn't really be remembering addresses anyway. You should be using DNS to make friendly names for your addresses instead. Subnet works the same way as I showed briefly before. It's just that we now have up to /128 when before we only had up to /32. IPv6 addresses can be auto-generated based on MAC addresses because there's so many bits in here. MAC addresses are 48 bits, so you can fit a MAC address in there, and I'll talk about that very soon. They can also be randomly generated with privacy-preserving extensions, which is very interesting. And more importantly, the most important point is that there's enough IPv6 for every device in the world. And it restores the end-to-end principle, because since there will be enough addresses for everyone in the world, that means we won't need to be hiding all sorts of devices behind one IP address. Every device on your LAN, for example, will be able to have its own IP address. There are three types of IPv6 addresses I'll talk about. We have the GUAs, which stand for Globally Unique Address. These are what you're going to be using, really, in IPv6, the standard addresses. These are most like an IPv4 public address. And they're in the range 2000/3. We have ULA, Unique Local Addresses, which are non-routable IPv6 addresses. These won't show up on the global internet. They're a lot like the IPv4 private addresses, except that in the specification they must have random bits in them, which prevents them from colliding. So even if you use two ULAs on two different networks, you're never going to end up with the same IP addresses. That's an important point, because something that would happen on IPv4 is if you had two networks, two LANs that were both using 10.0/8, and you wanted to connect them with a VPN, for example, you'd have the issue where addresses are being used on both sides of the connection and create conflicts. That's not the case with ULA. And the final type is the link local IPv6 addresses, which start with FE80/10, and these addresses are on every single interface of your system in IPv6. And the reason why that is so that you can connect two computers without the need of a router, for example, on both ends, and they both automatically will configure an IP address, and you'll be able to talk between them. So this is used mostly for talking between a computer and a router directly on the link, or between two computers, or things like that. The equivalent for this in IPv4 is 169.254, and it's really not used a lot in IPv4, but it's used a lot in IPv6. So once again, we have some fail here in my presentation. I'm actually going to see if I can fix this. Where are we at? Slack. Anyway, I'm not sure. I'm not going to detract from this too much. We can see the text here anyway. Slack stands for Stateless Address Auto Configuration, and it lets devices choose their own IP address instead of relying on a DHCP server on your router to keep track of the leases. This is desirable because there's just less configuration to do, and devices choose their own IP address. So all the router does is that it announces the prefix, which is the first few bits of the address that identify the subnet, and then a computer can choose its own address. And this is really useful because we can use something called EUI64 with Slack to generate a predictable static IP address for an interface. So the actual math in this image here is really irrelevant to this presentation, but it's just to show you that we can take the MAC address of an interface. This is something that's in hardware and usually doesn't change. And we can stick these bits right into an IPv6 address by putting FFFE in the middle. And with EUI64, anytime you plug this computer into any IPv6 network, the address that's going to be generated here is always going to be the same. So you wouldn't need to configure a DHCP server like an IPv4 or anything like that. You could just plug in a computer and immediately know what its IPv6 address is going to be. And there are some privacy concerns for this, obviously, because you could be tracked on the internet through your MAC address, since this IP address never changes. And because of that, Slack was improved in RFC 4941, and they added a privacy extension, which creates multiple randomly generated IPv6 addresses that are frequently rotated. So when this is enabled, this is like enabled by default on Windows 10 and I think Mac OS and Linux. It's pretty standard. It just means that you're always going to be using different IP addresses to change the web. So you cannot be really tracked by IP addresses because they'll change every few hours. And since there's so much space in IPv6, it's a great use of all that space. You can constantly rotate your IP addresses.
I have a question. Considering MAC addresses are 48 bits, what will happen when we run out of MAC addresses?
MAC addresses? I actually don't know. That's a good question. I don't know how MAC address, how the distribution of MAC addresses works. So I'm not really in a good position to answer that. Sorry.
Okay. Well, my question was about is there any other protocols to use instead of Slack?
Instead of Slack, yes. I believe it got cut off. Yeah. Sorry, it got cut off in my other slide. You don't need to use Slack. This is one scheme of configuring IP addresses. There's also DHCP-v6, which is much like the IPv4 version of DHCP. Your router assigns IP addresses to your devices, and that can be used instead, or you can just use plain static addressing. But Slack is more like the idiomatic way of doing it in IPv6. Of course, in enterprise settings where you need to keep track of who has what IP, DHCP-v6 is preferred, because on Slack, the router doesn't control the assignment. It's the end device that chooses what IP address it wants. Now I'm going to talk about how IPv6 addresses the end-to-end connectivity problem. So what are the implications of using global unique addresses on every device on your network? To the uninitiated, this might sound kind of scary because you think that suddenly all of your devices are just exposed on the internet because they all have a public IP address. So what we need to understand is that just because we have a public and routable address doesn't mean that we're automatically exposed. So we still have a firewall on our router that would ideally prevent incoming connections to all of our IP addresses. So if we have properly configured firewall rules, we can open a port on a specific IP address and allow that connection. But by default, we would deny everything, and we would have the same level of security as your typical IPv4 deployment. It's just that we wouldn't need to hide devices behind an IP address since we have enough to just give them out to everyone. So the important thing here is that we can drop the whole public and private IP address designation, and we can think of them as routable or not routable. It's important to know that just because an IP address can be routable doesn't mean that it has to be routable. You can use global IPv6 addresses and never publish them over BGP, so they'll never exist in the global routing table, but they will still be usable for your internal network. And since we're using unique IP addresses on every device, the scenario where I talked about earlier, where we can't host multiple SSH servers or multiple web servers because they're using the same port behind our NAT, is no longer the case. Since we have IP addresses for everything, all of your machines on your network you could access via SSH on port 22. If you had multiple web servers, you could access them without a reverse proxy, things like that. And I'm just going to address a few also misconceptions about IPv6. So like I said before, IPv6 is not IPv4 with more address bits. It's a lot more than that. You can't just say that it's the same. There's additional there's just additional things I talked about. And also this is more of a misconception about IPv4. It's that NATs don't provide additional security. People think that because they're hiding behind one IP address that it makes their services more secure, and that's not the case. What's really giving you the security is the firewall in front of your is the firewall on your router. It's not the fact that you're translating your IP addresses. That's just breaking end-to-end connectivity and making it more of a pain. And also, like I said just before, using global IPv6 addresses doesn't mean your network is exposed. You don't have to route those addresses on the internet, and you'll have a firewall in place that's going to secure what's happening on your internal network from the external network. Now I'm going to talk about different ways that you can transition to IPv6, strategies used to migrate to IPv6 from IPv4 without, of course, disrupting whatever you've got going on in your network. So there's two big paths you can take that people take usually. You have dual stack networking or single stack networking with tunneling for whichever protocol you're not using. So I'll talk about dual stack first. Dual stack basically means that you're running the IPv4 network stack and IPv6 network stack in parallel. It's the most straightforward and easy path in my opinion, because you can just run both protocols in parallel. All of your software will prefer to connect over IPv6 by default, and whatever doesn't support IPv6 for any reason will just fall back and use IPv4. So in this scheme, you have every host in your network is going to get at least two different IP addresses, one of them being IPv4 and the other one being IPv6. IPv6 is preferred by every operating system, and IPv4 is used as a fallback. All major operating systems have mechanisms in place to make sure that if ever something's broken with your IPv6, that in pretty much any case you can gracefully degrade to IPv4 and you won't have a problem. Dual stack networking is also the simplest to implement because there's the least, there's the least just messing around with your network. Your existing v4 deployment is going to work like it always has, and you can focus on your v6. And it's good for home and office networks, especially because I say mostly home networks because there's a lot of like various tidbits like IoT things where the networking concepts are they're just not the main focus of the product, and they don't work well with IPv6 or things like that. I'm being told that there's static in my voice. Is that still the case right now? Alright, sorry about that. So it's the best for home and office networks because in these kinds of networks you'll find a lot of various devices that don't support IPv6 well, so you want to have an IPv4 fallback. Now, we have some fail again in my presentation, unfortunately. I'll talk about single stack IPv6 with NAT64 and DNS64. This is a bit of a more advanced use case, which is harder to implement, and it's mostly used in data center networks. And I'll go down here just to illustrate it. Basically how this works is that you drop IPv4 completely on your client right here. It only has an IPv6 address, and then every time a DNS request is made to go to a server, it goes to, instead of a regular DNS server, it will go to a special DNS64 server. Then this server does the query, and then they see, oh, it's responding with an IPv4 address, but we only have IPv6. So it's going to encode this IPv4 response into an IPv6 address right here using the special prefix 64:FF9B/96. And because IPv4 is only 32 bits, and in IPv6 we have 128 bits, we can encode the entire IPv4 space in just a little part of IPv6. So this here basically represents the entire IPv4 space for your application. And then your IPv6 only client will connect to this special address, go through a NAT64 gateway, which translates the IPv6 back into IPv4. And this is basically the same natting process that's happening, on a home network where everything is behind a private IP. So it will get some sort of private IPs where all the IPv6 behind it originate from the NAT's IP, but then it gets sent back into IPv6. Ideally, you'd want to avoid having to use this at all, but sometimes you have applications that still do rely on IPv4, so you want to have it as a backup layer. Then you have a special case here called 464X-Late. I'm not going to talk about this one much, but only because it's actually widely used in mobile networks, and it's quite possible that some of you on your mobile phones are using 464X-Late right now. What 464X-Late does is it provides native IPv6 connectivity, but it also gives IPv4 connectivity over the IPv6. So it's a bit like the other one where you can still access IPv4, but because in DNS64 you only have an IPv6 address, it means that if something is expecting an IPv4 address, it won't work. But with 464X-Late, you also have a private IPv4. So all this here you don't really need to understand the technical details. I'm just showing here where you would have native IPv6, and if you're using IPv4, you can still use it, but it goes through IPv6. The idea here is that we want to have IPv6 as the primary method of communication and IPv4 being a legacy method of communication that's still supported, but that could one day be removed once it's not required anymore. So now I'm going to talk about IPv6 deployments in the wild right now. What are people doing with IPv6? Google has a very useful graph on their website where they measure the amount of IPv6 connections to their service versus the amount of IPv4 connections. And to be honest, it's getting better every year. We can see that in 2009 there was IPv6 almost didn't exist, and now we're in 2020 and we're seeing almost 33% of Google's traffic being delivered over IPv6. The biggest IPv6 deployments worldwide right now are mobile phone networks, because those networks are the ones that have been NATed from the start. There was never enough IP address space for mobile phones. If you think of everyone, all these mobile devices, it really makes sense to switch to IPv6 for those. Next up, we got residential internet providers. They have a less good track record of providing IPv6 to customers, but it's starting to change. There's lots of deployments going on everywhere in the world, slowly being rolled out on residential networks. And it's been discovered through some studies that the biggest lack of IPv6 connectivity right now is attributed to corporate networks, which are stuck on IPv4 and don't have v6 access. If we zoom into these graphs, if we zoomed in really far, you'd see that there's these constant up and down spikes, and those correspond to what they call the 9 to 5 work cycle. They notice starting 9 a.m. people go to work, and then they don't have IPv6 at work, so that number goes down, and then they come home, and then their mobile provider has IPv6, or their home network has IPv6, so they use IPv6 at night. And these are what these spikes are from corporate networks not having IPv6 in their networks in general. There's also large tech companies that are going IPv6 only in their data center. Previously, you would have widespread NATs in data centers, lots of servers using private IP addresses, and that would be complicated to manage because you have some servers need external addresses, some servers need internal addresses, some servers have both. You get this mess of how do we access what, which address do we use. We could just switch to IPv6 and we would have so much more capacity for adding more addresses. We could address all of our servers with a single address. So these companies here like Facebook and LinkedIn have taken strategic bets for years on eliminating IPv4 from their data center networks and running everything on IPv6. In fact, if you're accessing Facebook without IPv6 right now, you're going through a translation gateway at Facebook that's translating your traffic to IPv6 so it can be processed on their servers. And both these companies I'm mentioning because they have really good engineering blogs where their network engineers talk about the road they've taken to switch to IPv6 and implementation specific details, why they've done what they're doing and how they're doing it. Very interesting. I can provide links for those later. Now, there's also studies done by Facebook actually measuring if IPv6 is faster than IPv4, and it turns out that according to a study they made in 2015 using the Facebook mobile application, they noticed that people were loading their app from 20 to 40% faster on IPv6 than on IPv4 on their mobile phones. And basically they've attributed this to the lack of middle boxes and NATs and carrier grade NATs in the path between the user and Facebook. All these NATs that you go through, they add extra processing and latency to your traffic, and by using IPv6 and not having to go through those, you end up with a quicker path between your end device and the servers on the other end, which I think is a huge win. So because IPv6 is so widely deployed in mobile networks, it's great for companies like Facebook because the traffic gets less mangled. And finally, I'm going to talk about IPv6 deployments in Canada. There's a few mobile networks that have IPv6. I've tested this personally on Rogers, and I know Bell also has it. If you have any of those providers, when you're on LTE, you are using IPv6, and they use 464X late, which I talked about earlier. So you get native IPv6, and if ever you're accessing something on IPv4, you're actually going through a NAT to access that content. There's a few residential networks, such as Rogers, TELUS. I don't think we have those in Quebec. TechSavvy has it on DSL. And just recently, I just tested this like a few weeks ago. Videotron Helix, only on their Helix server, on their Helix service, they have native IPv6, which is great. For those who don't have native, there are tunnels. Videotron has had 6RD. What these do, they're not real IPv6. They give you IPv6 connection, but they do it by tunneling IPv6 over IPv4, which is the opposite of what things like NAT64 and 464X late do. So they're not really useful. They're not useful in the grand scheme of things, but they're still useful to provide your internet, your local network with IPv6 if you really can't get it through your provider. I personally use Hurricane Electric's tunnel broker at home, so I can get IPv6 because I'm on TechSavvy cable and they don't offer it. So anyway, and the big thumbs down for this presentation, naming and shaming the Canadian providers who don't have native v6. Videotron cable, non-Helix, that's a thumbs down. No IPv6 there. They get minor thumbs up for their 6RD tunnel, but still. Bell 5, another one that I really don't understand. They're providing fiber to the home, super fast gigabit speeds, 1.5 gigabit, but they can't give you IPv6. Thumbs down. TELUS Mobility, also another thumbs down. Videotron Fizz, I forgot to include it there. That is also no IPv6, and you're going through carrier grade NAT. It's literally the worst case scenario. So I really hope that these companies step up their game in the future and decide to provide v6 for all the reasons I've gone over now. So anyway, that's it for my presentation today. I found this funny artwork here where they're going anti-RFC 1918, which is the private address space in IPv4. It's saying that you should be using 2000:3 instead, which is the global IPv6 range right now. So anyway, thanks for watching, and if you have any questions, I'm happy to answer. Thank you.
Thanks for the talk.
And I'll encourage you to keep enjoying your beer, whatever you're drinking. You're welcome, reindeer. And if you have any questions in the future, I'm always going to be hanging out here. You can ask away. And for those who haven't weren't able to participate or missed the live talk or whatever, I've got this all recorded, and I will be coordinating with the moderators to get the file published. And I'm also gonna fix my slides and publish those too, so no worries about that. It's unfortunate that I had a little fail at the end, but that's what happens when you don't test. Just gonna check the other channel here. Nope, looks like we don't have questions. Or do we? Nobody understood. Very nice meme.
Yeah, I have a question.
Yeah.
Do you think it would be a good idea to, when you're looking for a new ISP, say, to aim for an ISP that provides IPv6, or is it fine if for my own network I still use IPv4?
Well, I'd say, of course, it's great if you can ask your provider or look for one that supports IPv6. I mean, of course, it's also a question of requirements. I personally really enjoy having IPv6 because I enjoy playing with servers, and I host a bunch of stuff at my house, and IPv6 allows me to get unique addresses for all my servers. It's really useful when you're hosting things to be able to get a direct end-to-end connection. It's for some people, IPv6 isn't really a requirement, and it's fine if they don't have it, but they're going to be missing out maybe in the future as more IPv4 gets phased out and we get significantly better speeds and routing on IPv6.
Okay, because I was thinking, should I be recommending IPv6 for my parents? And you said they probably don't need it, so.
Yeah, like for your parents, they probably don't need IPv6, and it's not a big deal that they don't have it. I'm thinking for more technically inclined people, that's where it makes a difference.
All right.
You know, unfortunately, there's a lot of places in the world where people don't even have the choice to choose between different service providers, and like, you know, IPv6 isn't even on the table. It's more like, you know, what can I get? But if you can find something, if something's available with IPv6, I would definitely recommend that you choose it over something else that doesn't. That's all I'm
Okay. Yeah. Thank you.
All right. Well, thanks very much once again for listening, and hope to see you next time if I do another talk or something like that. Thank you for being a good audience.
Thanks, Tristan. Have a great day.
All right. You too, guys. See ya.